What time is it? It's science time!
Science time. Let's all stop and just unwind. 1, 2, 3, 4, here we go. Learn so much your brain explodes. Lessons so cool, so fresh. Beat so big you'll lose your breath. Learning facts and real cool stuff. Scream for more, can't get enough. It's science time. It's fun, you best believe. Explore and learn new things. Come and join me, please.
I'm Mr. C, and this super smart group is my science crew. Lila is our notebook navigator, Alfred is our experiment expert, Riley is our dynamite demonstrator, and London is our research wrangler. Working with my team is the best and makes learning so much fun. Actually, you should join us. Today, we're talking about the laws of motion. What time is it? It's science time! Welcome back to DIY Science Time. Welcome back. Let's have some fun. Let's bust a rhyme. Welcome back. We're here together. Yes, it's true. Welcome back. I'm glad you're part of my crew. Welcome back, everybody. My name is Mr. C, and I'm so excited to be here today with all of you. We are going to have some fun learning about Newton's laws, and we're going to be talking about Newton's cradle at the end of the show. But before we get to this, we definitely have to talk about Newton's 3 laws of motion. So are you ready to get into motion? Because Alfred has some materials you're going to need in order to build one of these.
We're going to get into the swing of things today, building our very own Newton's cradle. You'll need the following materials to follow along: cardboard, straws, marbles or steel ball bearings, string, scissors, hot glue, and of course, your swingy, springy science notebook.
A science notebook is a tool that every scientist should have, and it gives us a place to record all of our learning. Taking good notes and being organized allows us to be better scientists. A science notebook allows us to go back and review all the data and information we've gathered during our experiments. Plus, it allows us to share results with other scientists who might be interested in learning more about what we've discovered. Whenever you see the notebook pop up on the screen, like this, it's a reminder that this is a good place for us to jot down new information. You can see I've already added a title and a list of materials for today's activity. Our crew is still going to have lots of information to collect and organize as we go through the experiment, so keep your notebook handy. Most importantly, the more you use the science notebook, the better you'll get at taking notes and recording data. If you don't have a science notebook yet, download a copy of Mr. C's science notebook from the website.
We're talking about three laws of motion. Sir Isaac Newton used these 3 laws of motion to describe the relations between the forces acting on an object and the motion the object experiences. The first law, the law of inertia, says that objects at rest will remain at rest unless acted upon by an outside force, and objects in motion will stay in motion unless acted upon by an outside force. Newton's second law of motion says that acceleration happens when a force acts on an object. Law 2 is also known as F equals ma, force equals mass times acceleration. And the third law is also known as the law of action and reaction. For every action, there is an equal and opposite reaction. This means that forces are always found in pairs. There we go, and we are set. And as you can see, I have a quarter, a card, a cup, a card, and a glass. And the question is, can I get the quarter to fall down when I flick this? Or is the quarter going to shoot off when I flick this? First law of motion, objects at rest stay at rest unless acted upon by an outside force. Here's the force. In 3, 2, 1. Oh. Oh. Yes, it worked. Did you see that? Everything fell down. I flicked the card horizontally and the card shot horizontally away from the system. But the quarter that was stacked on top, it did not shoot off of the card. Instead, it fell. And once it got into motion, it was going to stay in motion and go all the way down to the table, But guess what was in the way? The cup. The cup was pushing up, right? And so the cup stopped the quarter in its place. And could you make it taller? Could we build a super tall tower with a whole bunch of cups that we can, and it would fall straight down? I don't know. Oh, so close, so close. There you go. Build your own tower and see how many cups you can stack and still get the inertia tower to work.
In 1968, the United States made it mandatory for car manufacturers to have seatbelts. The seatbelt prevents you from moving forward during a crash, which helps keep you safe and secure in your vehicle.
Grab a thin coat hanger and bend it into what looks like the letter N. Carefully connect 2 tennis balls to each end. Try to get the system to balance itself on your finger. Once you've got it balanced, you're going to place it on your head.
It's so windy, I hope it works though.
Now try spinning in a circle. The tennis balls will mostly stay in place because of inertia. Since there is little friction between your head and the metal hanger, you can spin the hat and it remains in place. How many spins can you make before the tennis balls start to spin too?
Oh, it works really good. Inertia. F equals ma, or force equals mass times acceleration, Newton's second law. That's right, I've got a fun little experiment that you can do at home. Check this out. I have 2 blocks of wood. I cut this down so that they're each the same size. That way you get 2 equal blocks. Now what you do is, you can see here I connected the 2 blocks with these little hooks, and I put a little piece of tape here so the rubber bands don't come off. Bing, bing, bing. And then I have these little screws on the side with a piece of rubber band here so that I can add additional mass to the system. And I did this twice, and then I connected it with a rubber band in the center. These 2 wood carts are a system, and the rubber band is the force that's acting on each of the carts. So because I connected these 2 rubber bands together, we can say that it's equal to basically 1 longer rubber band. You can see right here, before we actually stretch them, they're each about 5 inches from the center. So if I stretch them out, let's say 10 inches from the center, and I let go, let's see where they collide. Oh! Oh! I had it upside down. I had the rubber band facing down, so it created lots of resistance. All right, I messed up. Let's do it again. Make sure the rubber bands are up and out of the way so they can slide appropriately. All right, here we go. I'm gonna slide this out. 3, 2, 1. Oh, did you see that? They hit right in the center. They both collided right in the center. Now, the equation F equals ma, or force equals mass times acceleration, means there's a force acting on this block, each of the blocks. The force is equal. Since the mass is equal, that means the acceleration also has to be equal for both blocks. So when we let them go, they should collide right in the center. But here's the question. What might happen if we add additional mass to one of the sides, like this? Think about that. What might happen to the acceleration if we add additional mass to this side? And you can see here, I have this little rubber band piece here to keep it all intact so it doesn't slide off. All right, so we're gonna start it here. They're about 5 inches from the center. I'm gonna stretch them out to 10 inches again, both of them. And now when I let go, let's see what happens. 3, 2, 1. Whoa! They collided right here at about the 5-inch mark on this side. So the force was still equal on both sides, right? The force stayed the same. However, this one has less mass. This one has twice as much mass. This one accelerated basically the same speed it did before, but this one, because it had twice the mass, accelerated at half the rate. And what's interesting, if we do it again, it goes half the distance before this one runs into it. They smack each other right at about the 5-inch mark. So, what happens if we add additional mass? Let's try it again. Do you think it will accelerate faster or slower? Do you think it will travel farther or less? Okay, woo, that's getting heavy. Here we go. Stretch it out. 3, 2, 1. This one barely moved at all. The force of this rubber band isn't moving this heavy block of wood very well. But the small block, the one that hasn't been changed, is still accelerating at the same rate. So give this a try. You can do all sorts of things. You can make some really cool adjustments, like what if you use a stronger rubber band now? Will it have the same impact on the system? What happens if you take this one, this block, whoops, off, and what if we put it onto this other side? And now, in theory, our system is equal again, same force. The mass is double on both of them now. So the acceleration should be the same because the systems are the same. And they come right back to the center. Give it a try. Have fun exploring different masses to see how it impacts the acceleration, or change the force to see how it impacts the acceleration. Force equals mass times acceleration. Newton's second law!
The average freight train is about 1 to 1 1/4 miles in length. A freight train moving at 55 miles an hour can take a mile or more to stop after the locomotive engineer fully applies the emergency brake.
Why is it so hard to wake up in the morning? Newton's first law. A body at rest wants to stay at rest.
I love toy cars. Toy cars are so much fun because they allow me to explore physics. And this actually is going to allow us to take a look at Newton's third law, which is equal and opposite reactions. For every force, there's an equal and opposite force that occurs. What does that mean? Well, let me show you. I'm gonna take this car and I'm gonna get the motor going. I'm gonna put it down, and when I let it go, the car goes that direction. But would you believe me that the tire is pushing this direction against the table? We'll call it the earth, like on a real car. It's pushing this direction because the tire is rotating. And when the tire hits the ground, it creates friction, and it's pushing backwards. So when it pushes backwards, the table is actually pushing the car forwards. It's kind of weird to think about, but that's what's happening. Car pushes backwards on the table equally pushes on the car and pushes it forwards. So, I have a little experiment for you to give it a try. We're gonna take all of these colored pencils and we're gonna put them down on the table. And I'm gonna take this piece of cardboard. I'm gonna put it right here on the table as well. I'm gonna wind up the car again, just like I did, and I'm going to put the car right here onto our cardboard. And the question is, what is going to happen to the car and the cardboard? Will the car go forward? Will the cardboard go forward? Will the car go backwards? Will the cardboard go backwards? Or will they all just stay in the same place? What do you think is gonna happen? Let's give it a try. I'm gonna wind it up just like I did. Did you see what happened? When I put the car here, it shot the cardboard out. The car essentially stayed in the same place. It moved a little bit, but it mainly stayed in the same place. That's because this time, the car is pushing against the cardboard, and the cardboard is pushing against the car. The car is saying, I want to go this direction because I'm pushing backwards. The cardboard's saying, I'm going to push you forward because I'm giving you the same equal and opposite reaction. So, when I hold it like this, the cardboard shoots out because I'm a big enough mass to keep the car in place. It doesn't move. But we can set it up again. Whoa. What happens is, like I said, this doesn't move. This essentially, the system stays in place. The car stays pretty much in the center. The cardboard stays here as well. And eventually when it's about to run out, they kind of go in opposite directions. Third law, equal and opposite reactions. If you want to take this experiment outside, go outside and stand on the ground. Then, from a standing position, jump as far forward as you possibly can. You are applying a backwards force against the earth, and the earth is applying a forward force against you. Equal and opposite reactions. This allows you to move forward as you jump.
Grab a piece of string and pull it through a straw. Connect the string somewhere secure, like to a knob or door handle. Now blow the balloon up and tape it to the straw. When you release the balloon now, it has a specific path that it will travel. We can observe Newton's third law as the air rushes out. This is an action, and we see the balloon racing in the opposite direction. That is a reaction.
Legend has it that Isaac Newton was bonked on the head by a falling piece of fruit in the 17th century. I guess that might have been the inertial moment that inspired him to explore the laws of gravity.
Let's put our hands into motion and jot down some notes in our notebook. We've had a busy day discussing the laws of motion. I've added all 3 laws of motion to our notebook, and I've also included information about each of the experiments we conducted today. My head is spinning with all of this new information. Sort of like the Inertia Hat. I definitely think everyone should give that experiment a try. I wonder if changing the mass on the ends of the hanger would impact how it works. Do you think it would work differently on my head compared to yours? You should definitely give that a try.
And now we're going to build our Newton's Cradle. That's right, a Newton's Cradle basically looks at conservation of momentum and conservation of energy. What you need is a piece of cardboard. Now your cardboard may be a different length than mine, that's okay. Just take your cardboard and measure it out. Mine is approximately 15 inches long, so I'm going to use that as the basis. I'm going to cut 4 strips out of my cardboard. And when I do that, I'm going to make sure that each strip is approximately 1.5 inches wide. Now it's time to cut them apart. Your strips might be longer, or they might actually be thicker, but that's okay. It doesn't have to be perfect, and it doesn't have to be just like mine. For the first 2 strips, I'm going to split them into thirds, which means each section will be 5 inches long. And then I'm going to fold and create a crease at each of the markings. For the other 2 pieces, we're going to split them in half, which means we need to mark them at 7.5 inches and then cut them. These 2 pieces are going to be the base. These 2 pieces are going to be where we hang off our marbles. We need to cut off 5 pieces of straw, and we just want these to all be the same size. We want them close to the diameter of our marble. I'm just going to slide that across. So I have these 5 pieces here. Not only is this what I'm going to attach to the top of the marble with the hot glue, but I'm going to use this as a guide for spacing. You can see that they're roughly the same distance apart. So we're going to just put this into roughly the center of our piece of cardboard here. And I'm just going to mark 1, 2, 3, 4, 5. And now I have that, and I'm going to set this other piece along with it. And I'm just going to mark that so that they're exactly marked the same on both sides. Now I'm going to cut my cardboard about halfway down at each marking. These are the rails. So now we're going to actually start putting this together. So we have our rails, but now we need to attach the straws to our marble. So I'm going to cut this. They're going to want to shoot everywhere. I'm going to take the cardboard, and I'm just going to kind of make a divot so the marble stays in place. I'm going to put a little dab of hot glue on top. And then I'm just going to plop that on there, just like that. And always remember that when you're using something like a hot glue gun, that one of your science crew members are an adult to give you a hand. So we have our pieces here, and we're going to take the parts that were the slits, and we're going to glue them, hot glue them against our black lines. And this is going to ensure that everything is lined up. And then on the opposite side, you're gonna face the creases, the slits right at the other slits. Now we're gonna let this dry just for a moment. And I'm just going to take a small little piece. I'm gonna cut about just half an inch up into that side and do it on all 4 feet. So now that I've used these pieces to connect it, you can also, if there's a little bit of a wobble to it, you can use this to kind of balance it out, because we want to eliminate the wobble because we don't want energy to be lost to the system. All right, so now we have our structure. Look at that, it looks just like it. No, it actually looks really good. But now comes the final part. What we need now is some string. So you're gonna need 5 pieces of string, and it can really be any length. I'm going to just go out about 12 inches. And then all I'm going to do is use the same piece of string to measure it out again. All right, so now we're gonna take one piece of our string. We're gonna put the string through the straw. And this is going to be our first marble in the system. Now I'm going to place it into the third one, which is the middle, because there's 5. And what's nice is, because this cardboard, it's really tight, you literally just slide it into the groove, and then it holds it in place. I'm gonna bring it up a little bit because I don't want it to hit the crossbar. I'm gonna try to center it. There we go. So we're gonna do that 4 more times. And I'm gonna put this one in front. And then I'm just gonna pull and pull until I get them about the same. There we go. Get our 3rd marble in there. Two more. It's our last one. All right, so this is the actual magic about this design. This is the coolest part, is you can adjust the strings super easily. Literally by just adjusting the height of the string in the crease, or by giving it more slack. And you want them in the center as much as you can in the string. This one needs to come up a little bit in the back. All right, the moment of truth. I'm gonna pull back on this marble. Oh, it works. It worked. All right, let's try that again. I think I need to give a little bit of slack on these. All right, I think I got it this time. So the goal is to get it as straight as you can and also get them level, right? So that when one of the marbles hits the other, all of the energy is being transferred directly into the next marble. So let's see what happens now. That worked so well. That was awesome. Okay, here's the deal. Not only can you let 1 go, you can let 2 go to see what happens. 2 kicks off. You can even mess with 3. All right, I've got a little bit of work to do because you can see that it's a little bit wobbly, and I think that's impacting the way the marbles are swinging in the system. Oh, this was so much fun. Newton's laws. Law 1, law of inertia. Law 2, force equals mass times acceleration. Law 3, equal and opposite reactions. And now we have a Newton's cradle, which talks about conservation of energy and conservation of momentum. But here's the deal. If you don't have one of these yet, you need to hop online and download one right now. The Science Notebook allows you to record all of the information that we've done today because it's a great place to record that data and information so you can go back and check it out anytime with your science crew. What an amazing day. What an amazing day. Keep learning, keep having fun, keep exploring, and remember, science is wherever you are. See ya! Yeah, it works.
It's science time.
Ta-da!
It's science time.
I'll try it. Take 3. Oh, that's so much fun. Inertia!
It's science time. It's science time. It's so much fun.
That's the sound of motion. Newt.